of a capacitor to store electric charges temporarily. Actually, you can see that these charges will be stored, then it can be discharged again. Now, the strength of this will still be determined by the battery. You know that if this battery contains a lot of electron will come here, and a lot of positive will be built up, and potential will increase. You should start thinking. So now, what is the symbol for a capacitor? You already know what a capacitor is and the function and how it looks like. So now, what is the symbol for a capacitor? A capacitor is represented like this. Those two lines must be what? Equal, the same. If it is longer, then you are no longer talking about capacitor. So the next thing is we have what we call capacitance of a capacitor. So what is capacitance? Just like the same way you say energy. If I say what is your capacity, that means what can you do? Abby, do you get that? What is your capacity? What is the function of a capacitor again? So if I now say what is the capacitance of a capacitor, what am I saying? Exactly. What is the amount of charge that can be stored by that capacitor? A capacitor of 6 microcoulomb and a capacitor of 3 microcoulomb. Which one has a higher capacitance? Which one can store more charges? Do you get it? All these things are basic things. So now, capacitance of a capacitor is defined as the ability of a capacitor to store an electric charge or to store electrical charges. That is capacitance. The ability of a capacitor to store what? Electrical charges. So, there's one thing. If you notice what I just did here, you have written that definition. This is a battery or a cell. I'm using it. This battery has a potential. You remember from what we just finished doing? We said potential is the work done, Abby, in moving a unit charge from one point to another. So I can move all these electrons from here to here, Abby. Now, depending on the potential of this battery, if I have a 12-volt battery, that means that's the potential, that's the work this guy can do. He can move 12 units of charges in a particular time, or he can do 12 joules of work per unit charge for every one charge. It can move there. So if I have 3 volts, between 12 volts and 3 volts, which one do you think will work more? So we are now saying that, do you know that 12 volts will move a lot of charges to this place, Abby? Please listen so that I get the next thing I'm talking about. 12 volts will do what? Move a lot of charges to this place. 3 volts, more than 3 volts. So meaning that the higher the V, the higher the charges. Are you getting that? That means that capacitance, Q, is directly proportional to V. The more the voltage, the more the potential, the more the charges stored. And the capacitance is the constant. Because this thing cannot carry more than what it can eat. You can't, if I say, can you finish a bar? You can't, even if I go and bring a trailer of a bar, you can only eat the bar. That is enough for your capacity. Do you get that? So now, that's what I'm saying here, that Q is directly proportional to V, but the constant is still your C. That's CV. So you need to know that your capacitance is given as Q over V. That's a formula you need to know. I'm explaining that way so that you will know, because there are some ways in which students misplaced all of these formulas. Some students will say C is equal to Q, C is directly proportional to V. Higher potential means higher capacitance. No. Q is direct proportional to V. Higher potential means higher charges will be stored. Is that taken? Capacitance is just what that capacitor can carry. So now, C is here now. From what we have here, the units for capacitance is what? The unit for capacitance is farad. So if I ask you, what other units do you think farad can be? Yeah? Especially if you are writing UI. These are things you have to be careful of. Farad is also coulomb per volt. Shey you get? Because that's the unit of capacitance. So that's, we can also say or lele mean or coulomb per volt. Shey you get? And sometimes you can hear 1 microfarad. 1 microfarad is 10 raised to power minus 6 farad. 1 picofarad is the same thing as 10 raised to power minus 12 farad. 1 nanofarad is what? 10 raised to power minus 9 farad. 1 femtofarad is what? That's 10 raised to power minus 15. So you can be asked to convert first before you solve. So this is one question. One thing, one formula you need to know capacitance. So now, what are the factors that affecting capacitance of a capacitor? So what are the factors that affect the capacitance of a capacitor? Are you there? So let's see. I've built my capacitor to store enough charges, but the way I built it matters. I can have a capacitor that has the same plates and I didn't arrange it well. I might not get the full capacity. What am I saying? The first factor that affects the capacitance is the cross-sectional area. The cross-sectional area overlap of the plates. Just like I said the other time, you take two slices of bread, you want to put egg between them, but you are overlapping them like this. Egg will only occupy that part, and you want to toast it. But if you put your egg very well and cover like this, so if I take a plate, for example, and I take a plate like this, or I take a plate like this, and I take a plate like this, and I sandwich them. Look at these two plates. Imagine that these plates move down a bit. What I've drawn here, imagine it is here, and I connect the wire. Then I sandwich them like that. You know, when charges flow here, only these parts might be affecting this. Do you get that? But if they move up, then the area will be more. And so all the negative here will affect everything here. Do you get that? This thing is important so that you don't cram some formulas. There are mistakes my students have made in the past. And I used to tell them not to make that mistake. So for this now, that means only these parts might be charged up. But here now, a lot of places might be what? Charged up, because the area of overlap is bigger. If you understand what I've said here. So at the end of the day, that means that the capacitance of a capacitor will increase if you increase the what? The area of overlap. That means C is directly proportional to A. That's number one. Number two, imagine I take these plates. The next one is distance between plates. Are you following? Imagine I take these plates that I want to overlap, and now I took one like this, then I took one like this, and I took one like this. We just did electrostatic force. Look at the distance here, and look at the distance here. Between A and B, A setup and B setup, which one do you think will help me to store my charges better? A. Because all the electron I get here, and this one is too far for this one to send away. Do you get that? So you don't want them to touch, but you still don't want them to be too far. So the higher the distance, the lower the capacitance. That means the lower the ability to store charges. Do you get that? So that means for distance, C is inversely related to J. Are you there? Can I rub this part? So now, in this case now, your C is inversely related to D, showing that the higher the distance, the lower the capacitance. But it's directly related to A. The higher the area of overlap, the higher the capacitance. The next one is nature. Nature of material. Nature of dielectric. So the nature of the dielectric you use will tell. Generally, dielectric usually increase capacitance. Presence of dielectric usually represent dielectric with E. Presence of dielectric usually increase capacitance. That means that separation is there to actually increase the capacitance. So, and that's just like the constants between them. So if you say that C is directly proportional to A and inversely proportional to D, if you introduce your constant, that means C is going to be A over D. Some students will go and say C, E, D over A. They make that mistake. And that's what I'm explaining. So if you get to this level, your brain will come and think, A is inversely. If area is smaller, the capacitance will increase now. If area is bigger, so you would have known that you have made mistake. Do you understand my point? So this is the formula, not this. That's why I'm taking time to explain that part. So if this is E naught, that means nothing is between them. We call it free space. So E naught is called permittivity of free space. Permittivity of what? Of free space. That's what E naught means. And I think that's 8 point something, 8.85 times 10 per minus 2 or so. So those that can remember, I don't know if that's correct. Then, if I now put a medium, there are different mediums you can put in between them. There are different ones. So depending on the medium you put, if you put a medium between them, it can just be any material. So permittivity of that medium is given as relative permittivity multiplied by permittivity of free space. So you can simply say that relative permittivity is equal to permittivity of medium over E naught. That's relative permittivity. This class I'm not fast though. This is a normal class. I'm not fast actually. Aside I'm not listening to you. And I'm still listening to you, I'm still asking you. Do you understand? If I do marathon class for you, I'm not fast too, so I'm still trying my best to carry everybody along. I'm still explaining. Capacitor, why explain? Timothy for formula, Timothy formula explain. Then we'll move on to the next. I'm still drawing. I'm still explaining. So if you are not learning, maybe you are the one that closes your mind. But if you follow what we are saying, definitely you will learn one or two things. So I'm not too fast. So the nature of the dielectric can tell you what can increase capacitance. So the formula. So which means that I can introduce E medium. I can put it in this formula. That if I put a dielectric between, then that's going to be ER multiplied by permittivity of free space multiplied by A all over D. So that's the formula. So which means every time you put a material, it will increase by a number. That number is what we call the relative in relation to when it was just free space. You know, if I have, let's say the capacitance of a capacitor is 3 microfarad. If the relative permittivity is 3, what will be the new capacitance? Like everything here gives me 3 microfarad. So that means that what we are, if I put relative permittivity of a medium that is 3, what has it done to that capacitance? It has increased it 3 times. That job that capacitor can do has been multiplied by 3 times. That means it increased capacitance. So in that case, I can just say C is equal to relative permittivity is 3 into everything here, which gave me, like might have been what to be your calculation, she gets. I'm just summarizing that story. So it's multiplied by 3. So this, let's say this is C2 and this is C1. C1 gives me 3 microfarad, C2 gives me this. So C2 is 3 times C1. That's what I mean by relative. So it is 3 times more than C1. C1. I don't know if you get the logic I'm putting behind this story. This is what I'm saying. Let's say you do a calculation. Let's even say that, okay, let's take a drill. A capacitor of cross-sectional area and this is where you have to also be careful. Most times they test how you convert units, especially for way you hear. They don't like giving it straight. They want you to convert a unit from one unit to another unit. So if you are not used to unit conversion, you might really go not yet in the exam. So let's say of cross-sectional area, units or area, meter square. Abi, that means you have to convert your millimeter square to meter square. It's as simple as that. And of cross-sectional area is separated by a distance of 2 nanometer. What is the capacitance? What is the capacitance of the capacitor? What is the capacitance of the capacitor when the dielectric is a free space? Is a free space. That's the first question. Compare when the dielectric is relatively thin. When the dielectric is relatively thin, compared when the dielectric is relatively thin. That means that I should compare the capacitance when it was a free space to the capacitance when you are using a dielectric material that the relative permittivity is 3. Just for you to quickly understand that. So let's do that. So how do you solve it? What's the area? 5 millimeter converted to meter square. What will it be? What you can just do is that you know that milli. What's milli? Then you square it. Milli is 10 raised power minus 3. Then if you square 10 raised power minus 3, that will give you what? 10 raised power minus 6. So that means this is the same thing as 5 times 10 raised power minus 6 meter square. You converted the milli, which is 10 raised power minus 3. But you know the square affects both of them. So that milli, you now square it. Then that gives you 10 raised power minus 6. That's the conversion. But if you don't know, you can also do it this way. 1 millimeter gives us 10 raised power minus 3 meter. Abi? Then square both sides. Then this will be 1 millimeter is equal to 10 raised power minus 6 meter square. Abi? Then you now put your 5 millimeter square doing your conversion factor divided by the one that you want to cancel with statement. Abi? Then 10 raised power minus 6 meter square. Then this and this one. That will give you 5 times 10 raised power minus 6 meter square. But Yoruba we always say something. So instead of doing all of this, is it not the same thing I've done here? So you have to be smart. It's not everything in the exam that you have to say when 1 millimeter equals 1 centimeter, 1 millimeter equals 1 parameter. Just look at it critically. Input what you are supposed to input, then move on. So, but that's the way. So that's the only problem you can have here with way you major. They want you to first convert before you use your value. So they want to test your knowledge of unit conversion. So can we move on? So now that we have our area, we have our distance. What's our distance? Linear conversion is always easy. This what's nano? 10 raised by minus 9. So that means that D, which is 2 nanometer, is the same thing as 2 times 10 raised by minus 9 meter. Shake it. You don't need to square it because it's a linear conversion. If it is square, then you will square this one too. And that will give 10 raised by minus 18. As simple as that. So now you can say C is equal to E naught. You know they said that we should find the capacitance when the dielectric is a free space, Abby. So that would be E naught A all over D. And what's our E naught? 8.85 times 10 raised by minus. I'm not sure if I can still remember that. Is it correct?
Yes.
Times A. What's our A? 5 times 10 raised by minus 6 all over. Are you there? JP1 is there. YouTube. Is what watching from India. Oh, okay. A lot of Indian camera. Hi, my Indian friend. Hello, my Indian friend. I love Indian mathematician. So for D, this is what? 2 times 10 raised by minus 9. Abi? So you can go on to divide and cut and do whatever you want to do. So now we are teaching from Nigeria, sorry. You know Nigeria does want basketball. So I'm teaching from Nigeria. We are good at everything in Nigeria. We are good in corruption. So we are good at everything. And then female Nigeria just won football. That's the female nations cup. Is it not West Africa? Our female basketball team just won the basketball competition. So when next we face India? So let's go on. There's an history that says that Indian guys won us 99-1. I know it's a lie. We are better footballers than Indians. You can come to me. 20 Abby. I know we just solved this one, so we don't need to start again. And what's our year? 3. So that means that C is going to be 3 into that thing you got. 22.125 times 10 raised by minus 9. So what does that mean now? That means that the capacitance with the relative permittivity has increased 3 times the initial one. Do you get that? Right, do you understand now? So can we move on now? Yes, sir.
You said your teaching method is fantastic.
I wish I can speak Indian right now because my heart is melting. So can we move on? They are my people. So can we move on? You can get the final answer. So now, let's come back to class. I think that people online will be learning better than you. Are laughing. You're laughing. So now, the next thing is, what's the... We just finished all the factors, I mean. So let's look at combination of capacitors. So combination of capacitors. Imagine, can I run this part? Are you true? Yeah. What's the time? 12:15. We're almost through, but this part is the part that is to waste time, but I'm not going to waste time. just get it right. Can I rub the board? Oh yeah. I see it up. Can I rub this board? So let's say I want to combine capacitors. Let's say I need a 5 microcoulomb capacitor. Please listen to this. I need a 5 microcoulomb capacitor in my electronics, whatever. And at the end of the day, I looked into my workshop. I only have 3 coulombs and 2 coulombs. But I need 5. What will I do? I need to find a way to join them together to give me 5. If I use 3, it won't serve what I want. But I need 5. If I need less than 5, I must find a way to combine 3 and 2 or whatever to give me less than 5. If I need 5, I must find a way to combine them to give me 5. And that's why the combination comes in. So there are 2 ways you can combine. If I want to combine the 3 and 2 to give me 5, I will combine them in parallel. That will be equal to 5. So let's see. The only thing you now need to know is how do you combine in parallel and how do you combine in series. So I did a battery like this the other time. Let's say this is my plate, sandwiched. Then I have another plate. Then I have this. Then I have a potential source. Now, when electrons start moving, everybody get this right now, please. When electrons start moving, they will get to this place and load up. Abi, if I have another capacitor here, sandwiched. This thing is important because when you are doing calculations, there are things that will be ringing in your brain and will make you to express yourself very well. This is one capacitor, let me call that C1. This is another capacitor, let me call that C2. The number of electrons when they get here, what type will they load up, Abi? And at the end of the day, they will send away electrons from here, from where I started from. The electrons from here will be, then this will become positive, positive. Let's just say 5 based on this part. So let's say 5 electron leaves. If 5 electron leaves, what is the number of electrons I'll get here? Are you following? If 5 electron leaves this place, how many will get here? You know, it's still the same parts. 5 will also load up here. How many will this one send out again? And that will continue. I hope you're getting something. So now, any connection in such a way that everything just goes in one single part, we call it series connection. You will see the difference. The electron gets here, then after sending out, everything is still part of the same wire. But let's look at this difference. One capacitor sandwiched with another capacitor, it is sandwiched. Then they are both connected to a source of battery. Look at the difference here. This is the negative part, the positive part. The electrons start moving, they start leaving this place. And as they start going, when they get here, that's a junction. If all these electrons are negative, if all of them get here at the same time, do you think that all of them will be waiting that this is the way I want to go? Since when they get to this junction, some can decide to take care, Abi, some can decide to take care as the electrons are coming. Do you get that? Now, if I have 5 electrons, 3 might decide to go this way and 2 might decide to go this way. Which means that it's the 2 that gets here that will do the job. It's the 3 that gets here that will do the job. But here now, if the 5 electron leaves, the 5 that gets here will send away 5 here. 5 will also send. So the same charges can be stored here. I hope you're following. But here now, anytime you have a junction that the electrons have decisions to make on where to go, then at that junction we call it parallel connection. It does not matter what you are talking about, either resistor, either capacitor, provided that there is a junction for the electrons to take different paths. So when the electron takes different paths, then we call that parallel connection. When the electron takes a straight or single path, I'm only using electron, I could have been saying charges, but almost still saying the same thing. So when the electron takes a straight single path, then we call that series connection. So that's the difference. In this case now, do you now think, so let's say this is my C1. So in your questions, this is what they do for you. So they will just put C1, C2. So they will now ask you to calculate the effective capacitance. Abi, look at these two. Are they in parallel or in series? Parallel. The moment you notice a junction, do you get that? Look at this one now. C1, C2. Are they in parallel or in series? Series. Because whatever passed through this guy, we also pass through this guy. So we get to current electricity and we deal with it. That's what it is. Now, from what I just said now, the charge that will be stored here, let's say this is C1 and C2. Let me call that Q2. The charge that will be stored here, let me call that Q1. The charge that will be stored here, let me call that Q1. The charge that will be stored here, let me call that Q2. Or let me come back here so that you picture it. Q1 and Q2 here, are they the same? Yes. Yes. Do you agree they are the same? Yes. Because it's the same electrons leaving that is also doing the job here. The charge stored here, are they the same? No. How many got here? 3 electrons. How many got here? 2. So it now depends on which one wants the electron more as per capacitance. Do you get the concept? So now you understanding that, then all your problems are solved. So let's now analyze it properly. So here now, charges will be different. Here, charges will be what? The same. So when you are connecting your capacitors, you can connect your capacitors in series. So by now, I expect you to be able to identify which one is in series and which one is in what? Parallel. So when they are in series, that means that they follow like this. Are you there? When they are in parallel, that means they have a junction between them. So I can call this my C1 and I call this my C2. I can also call this my C1. I can call this my C2. This is the potential from the source. Let's say the voltage from the source. You remember something again. But let me ask you the first question before I get it mumbled up. In this case, if I tell you that the charges stored in C1 is the same as charge irrespective of their capacitance, the charges stored in C1 is the same as the charges stored in C2. Do you agree? Yes. Yes, because they are both in what? Series. So I can say for series, charges are the same. That means that Q1 equals Q2, right? For this one, the charges stored in C1 is the same as charges stored in C2. True or false? Yeah? False. The only thing that can make that to be true is when their capacitance are the same. Do you get that? Because when you connect them in parallel like this, it is the same potential for both of them. And if their capacitance are the same, that means their charges must also be the same. So I don't want you to have it at the back of your mind that it is always false, that the charges can never be the same. That's why I said that. So it still depends on capacitance. But for parallel, charges Q1 is not equal to Q2. And you know that, Abby, that's for parallel. Another thing you need to notice, just for simplicity, we said that potential is what? Work done in moving unit charge from one point to another, Abby. So if I'm moving charges from here to here, let's say I move from here to here, or let me even say from here. No, this is the let me make this part my negative part. So let's say I'm moving charges from here to here. You can't compare the distance from here to here to from here to here. Like, just for you to understand, moving it from here to here. That means I've done work from this place to this place, abi. So that means the work I've done across this place, I can calculate it. But that one is called potential difference. That is the work done in a circuit. You get that in the current electricity. But I just want you to get something right. Just from here. Potential is what? Work done in moving a unit charge, abi. So this battery can send electrons. So, and moving a unit charge across a distance. So I move it from here to here. At the end of the day, I want to move it from here to here. You know, if I introduce, I will have a distance. If I introduce that to the formula, I think that's my KQ over RB and all of those things. So I have a distance. So, but is it the same work that I do from here to here that we do from here to here? No. Just for you to just note something, which means that the work done here, V, across this one, is different from the work I'm going to do across this one. So I can call this my V1, I can call this my V2, which means that for series, my V1 is not equal to V2. But for parallel, work I'll do from here to here is the same work I'll do from here to here. So potential for parallel is the same. So V1 and V2, V1 will be equal to V2 for parallel. I hope you're following. It's because of the way I've drawn it. There's a way parallel is arranged. You know, parallel means equal, everything on top of each other like that. Such thing you can think about. So I can say this is not equal to V total, because the total is the one charging it now. So it will do work here and it will do work here, so it will be depleted. But the work this one will do is the same thing here and it's the same thing here. So I can say V1 is equal to V2, which is equal to V total. We are going somewhere. So if they ask you, whenever you connect capacitors in parallel, potentials are the same, charges are not what? The same. All these are Roman numeral questions. When you connect capacitors in series, charges are equal, but potentials are not equal. Then, if charges are equal, for the first scenario, for series, Q1 is equal to Q2. V1 is not equal to V2, it's not equal to VT. But here, VT for series parts now, it is this battery that will do work in both of them. So the work done by that battery will be equal to the work done across the first capacitor plus the work done across the second capacitor. Shake it. And you remember, my Q is equal to what? CV. So I can say V1, if I make some of it now, V is equal to Q over C. So for V total, I can say V total equals total Q, Q total, all over C total. Shake it. We are just writing something. I can also say V1 equals what? Q1 over C1. Whereas I can also say V2 equals what? Q2 over C2. Are you following? So bring them into the formula. My V total is going to be Q total over C total, which is going to be Q1 over C1 plus Q2 over C2. Remember, all my Q's are the same. We already said Q1 is equal to Q2. It's the same total of electrons that left. How many left? 5, Abby. From what I described here, 5 left, Abby. 5 got here, 5 left. So that means that my Q total is the same thing as Q1, which is the same thing as Q2. Abby, if you follow this explanation. So now, my Q total, I can factorize that. I can have 1 over C total, Abby, equals factorize. These guys are the same. So I can bring them out. So I can say Q, let's just say Q1 is equal to Q2, which is equal to Q total. Let me still call them Q total. Q1 plus Q2 is Q total. It's the same. Q1, Q2, they are the same. Let me come back here. What's my Q total that left? Just for explanation, 5, Abby. What is my Q1 that got here? What's my Q2 that got here? So if I say this is 5 and I bring it out as 5, and this one is 5, 5, so I can bring that 5 out. Then I will have 1 over C1 plus 1 over C2. Abi? Because they are the same. So the 5 and 5 can go. So that means that if I see the same way, I can say Q1 and Q2 are the same. So I can just bring them out. Do you get that? So at the end of the day, my Q and Q, they are the same, just like 5, 5. So what will I have left? Sorry, I might write it here. 1 over C total will be 1 over C1 plus 1 over C2. So whenever you connect capacitors in series, your effective capacitance, we call it effective. So your effective capacitance is going to be 1 over C effective or C total, which will be 1 over C1 plus 1 over C2. If you want to make your calculation faster, you can do product over sum. If it is 2 involving 2, you can just say this is the same thing as saying C effective is equal to product. That's C1 times C2 all over C1 plus C2. That's another way you can solve it. So, but whenever you connect capacitors in series, that's how you do it. Is that taken? Then just remember these things. You can test your knowledge. So let's go on to parallel. So the other time now, I said I have 3 microfarad and 2 microfarad, and I need a 5 microfarad. Do you think connecting them in series will make me get 5 microfarad? No. No. One thing you will notice again is that the effective capacitance is usually less than C1 or C2. Let me take an example on that quickly. I have a question. I have a capacitor connected in series, 2 capacitors connected in series to a voltage source. Then C1 is equal to 3 microfarad and C2 is equal to 4 microfarad. Find this effective capacitance. All of you can identify here that they are in series, Abi. That's the first thing. If they are in series, how do I find the effective capacitance? 1 over C effective equals 1 over C1 plus 1 over C2. Abi? So now, but note something, I could have just done it straight. But let's just do it like this first. 1 over C effective is going to be 1 over 3 plus 1 over 4. Abi, find your LCM. LCM is what? That will be 4 plus 3. Abi, and that will be 1 over C effective. Abigail, don't go. Don't go. So C effective will be 12 over 7. Abi, 12 divided by 7 in fraction. Calculator, punch that. So here, that's 1 point something. 1.714 microfarad. So look at what I've said here. I said that the C effective is usually less than what? C1 or C2. They can ask you that. What did we get? 1.714. Is it greater than 3? Is it greater than 4? So whenever you connect them in series, the effective capacitance is usually lesser than. So I want to get 7 microfarad. I'm now connecting them in series. I've reduced the value instead of increasing it. Do you get that? So let's look on to parallel. So instead of now doing these stories that I've done here, in exam hall, you don't have all day, you don't have time. So you cannot be doing, let me look for SCM, let me look. Just say that your C effective is equal to product, which is just 3 times 4 all over sum 3 plus 4, and that's 12 over 7, and that's your answer. Is that correct? So you can see now which one saves you stress, which one saves you time, but you usually do it for 2 capacitors. So can we move on? So for parallel now, let's go for parallel. So for parallel, I told you that this part is the part that I might want to waste my time because I might need to explain some things. Because if you don't really understand this principle, I just give you formulas. you can hit a lot of questions and you won't be able to solve them. Because you can say find the Q inside this one, find the C inside this one. When this one and this one happen, what is the effect of this one? What is this and that? So you have to understand that part. And that's why I'm trying to take my time here. So now, for this aspect, we have the moment you understand principles in physics, it makes it easier for you. So my C1 now and my C2. You already said for this one, Q1 cannot be equal to Q2, Abi. So at the end of the day, so but your Q total will be equal to Q1 plus Q2. Do you agree? You know, if I leave here, 3 can decide to go here, 2 can decide to go here. So I can say the total Q now will be equal to what goes here plus what goes here. Do you get that? So now, my V1 will be equal to V2, which will be equal to V total. Do you agree to that? Whenever they are connected in parallel, same work is done across them. So now, I can now say that my Q is equal to CV, right? So I can say Q total is equal to C total multiplied by V total. Q1 is equal to C1 multiplied by V1. Q2 equals C2 multiplied by V2. Are you there? So at the end of the day, what are we going to have? You remember, Q total is what? C total, V total, right? Equals Q1 is what? C1, V1. Q2 is C2, V2. What is common here? V total is the same. So the same way, factorize V total here. So you can say C total, V total is equal to V into C1 plus C2. So this V and this V are the same. V total is the same as what is here, what is here. So at the end of the day, my C total will be C1 plus C2. So are you there? So my C total is going to be C1 plus C2. So now, if I need a 7 microfarad capacitor and I have 3 microfarad and 4, the best way is to connect them in parallel. And then the 2 components will give me 7. Shey you get? So now, which means that you need to also note that the effective capacitance for parallel is usually greater than C1 or C2. Do you agree? You know, if I put these 3 and 4 here, the effective will give me what? 7. 7 is greater than 3, 7 is greater than 4. All of these are things you can see in your exams and be free to express yourself. Matter I want to go. So that's that. So let's look at energy stored in capacitor. Then we'll stop here and the uses. Then I'll continue with current electricity if you want a break. But if you don't want a break, we'll continue with current. So I'll give you rough questions soon. Can I run this? So with simplicity, it's not hard. What is the energy stored in capacitor? Energy stored in capacitor is given as half CV squared. The rest can go its way. That is also equal to Q squared over 2C, Abi, which is also equal to what? Half QV, Abi. Those are the formulas for energy stored in a capacitor. So let's just use them so that we don't waste time. Those are the formulas for energy stored in it. You know how I got all of those formulas? If you plot your graphs, you will see that your Q is directly related to V and all of those things. You can find the area and all of those stuff. But just to quickly get it for you, I will go on. I shout. Most of the eye shots and all these skills. Can we move on?
Yes, sir.
So that's the energy stored. So what are the uses of capacitor? Those are the things you need to know. I said it at the beginning of the class. Capacitor is used in tuning to store charges. So it can be used in smoothing, not studio, smoothing. Smoothing is just like converting your AC to DC. Which other way, if you can still remember? Tuning is just for frequency regulation. So you're trying to change the frequency of the radio. Which other use again? Coupling, Abby? Coupling. I remember. So, prevention of spark, Abby. Prevention of spark. So that's all about capacitors, and those are the things you need to know. So if you have been following since morning, let's take questions, quick questions from beginning. Let's start. Drill. Question 1. Find the effective capacitance from the following. Find the effective capacitance. Have I been using microcoulomb? The ones we solved the other time, did I use microcoulomb or microfarad? Are you sure? Yes. So that's the first one. I don't know what this is going to look like, but just to give you. So you have to find C2. You have to find C2 in this place. You are given C1. Question 3. We've solved one on CA, so let me leave that one. So, answer true or false. First one. Total capacitance in series is greater than individual. Same for capacitors if you are listening to everything I've said, you should be able to answer all these questions. Charges stores are the same for capacitors in parallel. D. I need Julia's needs a 7 microfarad capacitor. Needs a 7 microfarad capacitors. But she has only 2 and 5 microfarad. How she connects to get 7. That's number 4 question. Number 5. What is the effect of the following on capacitance of the capacitor? What is the effect of the following on capacitance of a capacitor? A. Dielectric. B. Don't cram. Dielectric. B. The area of overlap. C. Size and shape. D. Distance between them. Distance between them. Are you following? That's what I said. I can get it. That's why I did. You know, this one, I just gave this one. So, that's all this reference now. So that's all capacitors. That's all capacitors. And you can now pick your books depending on which school you are going and which exam you are writing to start solving the questions. And if you have any questions, you can let me know. That's all. So which other one? So let's move on to current electricity. So we are through with 3 topics now. Electrostatics, electric field, we are through with capacitors. So current electricity. Current electricity is not much. With all the experience now, current electricity should be walk over for you. Except some deeper parts we have not talked about. So, which when I come back, I'll still talk about Kikon's law and all these other laws. Sorry, question. You can turn it. So for the first question, find the effective capacitance in this place. For the second question, find C2. if the total capacitance is 20 microfarad. Then for the third, I only gave this 20 microfarad, so I don't know what your answer might be. I just give those values off and play. So for this one, say it if it is true or false. Then answer question 4. Suliat needs a 7 microfarad capacitors, but she has only 2 microfarad and 5 microfarad. How should she connect to get 7 microfarad? What is the effect of the following capacitance of a capacitor? What is the effect of the following on capacitance of a capacitor? There are some other questions coming to my brain. But let's hold this for now. Number 6. Parallel. What effect does he have on the first and the second? That's the question. So think about that. Can we rub the board now? Yeah, let's be fast. My Samsung is here. Very connected. Are you true? Can I rub the board? Current electricity. All this will help you to understand better. That's why I'm giving you those questions to practice with. Then you can now pick your own textbooks and practice. If there's anyone you find difficult, you can let me know. And funniest thing is all these questions come out.
Sir,
Yes, sir.
is that I should read the last question?
I should read the last question. What is the effect? What is the effect? You know, it's weird when you can't see someone that is telling you to do something. What is the effect of disconnecting one of 2 capacitors? One of 2 capacitors. What is the effect of disconnecting one? There are 2 capacitors, so you are disconnecting one. What is the effect of disconnecting one of 2 capacitors on the other? What will be the effect on the other? When the 2 capacitors are in series or when the 2 capacitors are in parallel? So that's the question. What is the effect of disconnecting one of 2 capacitors on the other when in series or in parallel? So that's that. Are we through? Can we move on now? So don't forget to subscribe to our channel so that you get updates on the subsequent classes. You know these people? This person is in which school? Studying medicine in Futa. He's in Futa. This person should be 300 level now. He studied mechanical engineering in OE. Do you know this one? No. That brother that is there is the pioneer of life impact. Impact to floor. He used to do programs and going to our students are impactful, so you too can be impactful. So he used to go to all these orphanage homes to give them things. And if you see impact to block anywhere, that's promising. He studied nutrition and dietetics in UI. Followed by the only movements. So it will still come around. Maybe when we are doing the exams, they will come around. So that's Dr. Movement, study medicine and such. This is Simeon. A bookie like that. He knows book a lot too. He's also studying mechanical engineering at That is already Daniel. Daniel came to Primas from, he was not in science before, so when he came to Primas, he switched from commercial to science. It was so difficult for him, but he was persistent enough and he achieved his dream. So he studied mechanical engineering too, you know. That's the Obeni Bolu was always a troublemaker. He was always quiet in class, but he knows how to cause trouble. So he studied nursing in OAUTHC, Obafemi University School of Nursing. So this is Akiwale Benjamin. That's my own last born abroad. So he studied medicine in OAU, Obafemi University. That's engineer Kenneth, the Ken. He studied computer science, University of Ibadan. This is Toby Jeje Arebeshola. He studied civil engineering in Futa. Toby studied civil. He has always wanted civil, so he studied civil. The rest, I'm sorry, I can't see their faces. So this is Tolani. Tolani studying accounting in OAU. And she should be going to her 300 or 400 level. So all of them, everybody doing well. This is Ayo level. This is Linda. Linda got admission into universities. She got chemical engineering also in Lautech, but she said she wanted doing it.
You got computer.
So she now got computer engineering.
Computer in Lautech.
Chemical engineering in UAE. So a strong woman like Linda. She's going to maybe at 300 level too, but she's very strong. I like her. She's small, but she knows how to carry herself, and that's why she's going for an engineering course. She's vocal. So this is Sebuayo Mide. She faced challenges. She's in Unilag studying nursing. She faced a lot of challenges, and so on like that. Mama Yi. Challenges for
That's the officers. This one is
Are you studying food tech in UAE? This guy is studying nursing too in London. This person is studying medicine in UI. So you will get your own too. That's desire. Some of them face their challenges. They face their challenges, but they never give up. They never give up. and they achieved their dreams. Some of them got it once,
Yeah, you want to
and some of them didn't. She came from
I like
Ondo.
to like you.
She wrote jam maybe
Hey, don't pass shit. I will not
That's how we
be
increase now.
and she's going to 300 level. So you meet them, they will still come around. Our students used to come around and we give them opportunities to say that. So they will still talk to you, tell you about the challenges they face, so that you too you can learn about life. Are you through with the questions? So should we move on to current electricity now? Do you want to have a short break? What's the time? So if you are online, you can have a short break. You will streamline, you will create another channel. Or you can join the channel again after 30 minutes. What's the time now? I can't give 30. So by 1:30 we'll be back. So let's take chance from Mr. Felix. Mr. Felix. Okay, you can continue with the arts. So let's take our short break. So we'll see by 1:30. So that we'll complete current electricity and solve the questions. I also want to go and read. I have exam tomorrow. So if you are online, join us back in 1:30.